Hello, and thank you for showing an interest in my work today by choosing to watch this presentation. This was my individual engineering research project for my master's degree in Engineering Smart Systems at MMU. The project covered the requirements, design, and manufacture of a robotic device in a specific physiotherapy environment, resulting in a functioning prototype. Following this introduction is a 20-minute presentation detailing the timeline and work done in this project, which is succeeded by answering a number of questions and having discussions with the attendees of the call. This assignment quickly became a passion project of mine, so the presentation took place a few weeks after my master's had finished, when I had had time to reflect on what could be learned from this research. With the help of my project supervisors, Professor William Holderbaum, Dr. Penny Butler, and Richard Major, I was fortunate enough to present my work to both a variety of technology experts alongside frontline physiotherapy workers. Before we begin, I would briefly like to outline some context to aid your understanding of the problem area that exists, causing a device like this to be researched and considered. Firstly, on the screen you can see the device is supporting the child in the photo by their sides. The type of physiotherapy this machine is designed for requires holding the child in a fixed position at varying points along their trunk. This means it was necessary for the arms to be supportive at different heights and widths. I later go on to reveal similar devices and the selection of useful features that I would implement into my project, like safety design ideas. The talk then continues to explain how the 3D design was manufactured into physical parts using the additive manufacturing resources available to students and businesses at Print City. Documentation of robotic elements to the device are also discussed at great length, detailing why each electronic component was included and how it connected to the circuit and controls. And finally, before the call advances into critical reflection and answering questions, video demonstrations of the device in working order were presented and explained. So once again, I'm very pleased that you're interested in the work I've been supported in over the last year, and hope you also feel that discussions such as these can contribute to good causes in engineering. Thank you.
Thank you. So, first of all, I'm John, and I studied at MMU for 4 years, and I did a bachelor's degree in software engineering, and then went on and did my master's degree in engineering smart systems, where I then went on to go and meet Penny and Richard. So I'm interested in many fields of engineering, which smart systems was definitely a good choice because it exposed me to more of it. But the purpose of the meeting today is that I kind of fell in love with this project, I guess, because of the purpose of it, and it exposed me to, you know, your industry of physiotherapy and a bit of mechanical and electrical engineering. And I guess that I just wanted to demonstrate the potential for new technology in your field. Then afterwards, I suppose you all might benefit if a discussion sparks regarding any questions or further ideas for the benefit of yourselves, really. So that can be directed at me or amongst yourselves. But yeah, thank you all for coming again, and I'll get on with it. So yeah, the project was robotics and physiotherapy, specifically to do with aiding the SATCO. This was an individual engineering project and was supervised by William, who helped me remotely from MMU, and then obviously Penny and Richard. Penny and Richard are trustees of Optimi, which I'm sure a few of you at least are aware of, which is a targeted training website that contains resources to help people learn about physiotherapy with what I was exposed to with the resources that they provided to me was the SATCO assessment on children that have cerebral palsy and measuring the severity that they have it. So I'm sure I don't need to go into too much detail about this, as again, it is your field, but the segmental assessment of trunk control is an assessment that measures how severely someone has a condition like cerebral palsy. This can be quite difficult to do because sometimes the child will start wriggling, which makes it harder for the physiotherapist to control and is also uncomfortable for the child. So what I was introduced to on this project is the idea that a device could be created that would support the child's weight at a point below the physiotherapist's hands without harming the child or obstructing the session. So this would make it more comfortable for the child and make the results of the assessment more accurate. So firstly, I looked at some similar devices. The top left image that you can see is the Trust or trunk support trainer that can train and assist people to sit more stably through the improvement and strengthening of their trunk control using straps and counterweights. The design team claimed that Trust keeps wheelchair-bound patients who would otherwise fall over comfortable and secure during their PT testing. It also maximizes the range of their trunk movements beyond the typical amount that they would be able to do. The CP Walker exoskeleton is the top right image, and this was tested on 4 children, each completing 16 sessions with the device each. The aim was to test for improvements in trunk control as the patient became less reliant on the support of the device over each session. So the modes were position control, then leading over time to impedance control, and then eventually zero force control. So it would basically at first force them to walk in a pre-programmed pattern, and then over the sessions give them more control. And it found that patients overall increased their strength and speed by the final session. So the active trunk passive pelvis device is the remaining image, was tested on 10 healthy adults standing on an unstable ball, comparing their ability to reach and grab objects before and whilst being strapped to the device. So every adult improved their postural ability while in the device. So what I was mainly looking at when studying these devices was the health and safety features because, well, obvious reasons. And all of these features generally relied on the mechanics, the power supply, and the software development. So the biggest risk mentioned in all of these, was when the device swings and hits a patient or the physiotherapist, and the next biggest was when the device jams on a patient. So at least one safety release mechanism would be required in the proposed device. So briefly, I used the additive manufacturing facilities at MMU to create the device based on a design that I worked on using Fusion 360. The benefits of additive manufacturing are that it's more environmentally friendly because it uses only the required amount of materials, and it's cost effective and time effective because it allows a quick prototyping of parts. Additive as opposed to reductive, where you would start with a big block and then remove the parts that you don't need to then have a finished product. Additive, on the other hand, is layer by layer, just using the material that you need. So Print City is the facility that I spent most of my time at during this project. And the electronics I decided to do using Arduino because they're accessible, relatively cheap, relatively small components, and there's also a lot of documentation online. So the requirements, and I call them Moscow requirements because in software I learned that you can break everything down into a list of must have, should have, could have, and won't have. Must have is obviously a working mechanism. It should also be able to attach to the bench. It should have enough strength and balance to lift a child, at least one safety release mechanism. The electronics should be internal, ideally, and it should have some way of demonstrating the controls. It should also have a low cost because it is a prototype, and an interface that holds the child in the correct way, meaning the material that is attached, frictionally to the side of the child. I also read that a playful color scheme can make the child more enticed into getting into the machine, so anything to make it appear less daunting. And obviously it won't have sharp edges, places fingers can get stuck, uncomfortable materials against the skin, or the potential to hurt the child. So whilst things, there were problems with the projects at times, this was basically my list of requirements I would refer back to make sure I'm completing as many of these as I could. To define it medically, the risk classification, I believe that it would be somewhere between a class 1 or class 2A, since there is some danger of jamming or swinging, as mentioned before, but it shouldn't, there's no sanitary risk with blood infection or anything like that, so it would sit at class 1 or class 2.